Good morning. We start the session, and our first speaker should need no more introduction to those who were here on Monday at his concert. For those who have not been at the concert, I have to say a few words about Fredrik, and we talked about the three-unite brain, has three brains. He's a medical doctor. He's a professor of cognitive neuroscience, all on his own merits. And last but not least, he's one of Sweden's most renowned concert pianists, and he is known worldwide through several of his recordings. Decca and many other have published and issued his CDs as one of the most advanced interpreter of some of our contemporary composers like Sorabji, Ligeti, Kurtag, Stockhausen, and the list is very long. So now somebody who is not only a passive observer of the arts, of music, but who is an active musician, and at the same time a researcher of how music or other creative activities are produced in the human brain and are enjoyed by the human brain, will give you a lecture about all these things: music, creativity, and the brain.
Well, thank you very much, Balázs, again for your kind introduction, and many thanks both to you and to Jan for arranging this this wonderful event. It's a great pleasure to be here, really. So I think it's clear that we see a large and increasing interest in the neurobiology of music and other art forms in recent years. And this happens, I believe, for several reasons. First and foremost, of course, artistic behaviors are interesting in themselves. It's uniquely human, probably behaviors that engage an enormous amount of people. They're also universally human. We see arts in some form in all cultures over the world. So, of course, engaging in the arts can help to create connections, not just between East and West, but between cultures generally, bridging linguistic barriers and so on. And here we also have, of course, the deep and interesting, I think, problems of neuroaesthetics. Why do we categorize and rank things as ugly or beautiful? What's the neural basis of such judgments, and what's the sort of ultimate adaptive purpose of them? Another source of interest in the arts is, of course, the promise of finding new interventions that involve arts. And I think it's clear, we have a lot of evidence that there are associations between active engagement in arts and positive outcomes, such as cognitive performance or increasing social cohesion or well-being and health. Although I also think that we need more research to understand what are sort of the active ingredients here and what are the underlying mechanisms. However, I would like to focus today on a third aspect, really, and that's more the perspective of basic science. Because I think it's striking that it's almost difficult to think of a brain system that's not involved in artistic performance one way or another. So if you're interested in sensory systems, if you're interested in skill learning and motor performance, emotion, social cognition, and so on and so forth, looking at artistic behaviors and looking at artists as models can be very informative. So I would like today to give two examples of this, based on mainly on our own work, which focuses on music as a model domain. And the first example will be from skill learning and expertise, where I believe that recent work on music as a model has contributed in interesting ways to developing new models of expert performance in general that are more sort of multi-factorial in nature, and I'll illustrate that soon. And my second example will then be from creativity, where we use improvisation, musical improvisation as a model behavior to look at the creating brain. So music training and the brain then. This is a picture from a classical study by Krampe and Eriksson. It's a study of musicians and the relation between expertise and practice. And what you see in this figure is then the weekly intensity of practice in two groups of participants. The upper curve here are professional expert pianists. The lower curve represents amateurs. And what is plotted is the weekly amount of practice as a function of age of the pianists. And this is then based on retrospective estimates of how much they had practiced. So you can see how the professionals start earlier. This is typical. They practice more already in childhood. Later on, of course, you make your career choices and so on and so forth. So cumulatively, the area under these curves, of course, will differ very much. And this is intended just as an example. You will see similar things from other domains. You will see the same type of relations if you look not at retrospective practice data, but on log data from diaries. You will see this kind of relations if you measure actual expert performance in the laboratory. So practice is certainly one key variable behind expertise. It may well turn out to be the single most important predictor for a domain like music. And this, of course, has been a basic finding behind what I think has been the dominating theory of expertise, namely the deliberate practice theory of Anders Ericsson. So I will try to complicate this picture a bit later on, but certainly practice is important. And we see this, of course, if we look at the brains of groups of participants that differ in their level of musical practice. Here's an early study from the lab of Gottfried Schlauch, where they compared professional musicians, amateur musicians, and non-musicians, measuring regional brain volumes with voxel-based morphometry. And the blobs you see here, the regions, then represent regions that were found to have a larger regional volume in the professional musicians. So we see these effects where you would expect them in regions that we use during musical performance. We have here, of course, motor and premotor areas, auditory areas, but also here you can see Broca's region in the inferior frontal cortex and inferior temporal regions. And similar findings have now been observed in many studies. One interesting aspect of this is also, I think, that at least in part, these anatomical effects appear to be quite specific to the kind of musical training that you actually engaged in. Here's another example from the Schlauch group where they compared string players and pianists, focusing on the motor cortex and specifically on the hand motor representation in M1. And of course, string players and pianists do very different things with their instruments. String players use the left hand to shorten the strings. So you get a lot of fractionated finger movements with the left hand. You get a lot of stimulation of the fingertips of the left hand, whereas the right hand controls the bow. Pianists use both hands, but generally I would say the literature has more notes for the right hand. And what they reported here was that if you look at the hand motor representation, this hand knob or omega sign, this was more developed on the right side, which of course controls the left hand in the string players, whereas they found the opposite pattern essentially in the pianists. And of course the general points here are, these effects are specific to the instruments, but I also think that this suggests that that practice probably has a causal role here. Of course, it appears possible that you are somehow constitutionally, you have this kind of brain and then you gravitate towards the string instrument, whereas if you have this kind of structure, you are more attracted by the piano. But it seems likely that when you see this very specific phenomena, that practice has a causal role, I think. And this is also supported by this nice longitudinal study by Krista Hyde and co-workers. Most of the data in this literature is otherwise cross-sectional, so you have single measurements of brain structure and musical training. But here, what they did was to follow longitudinally two groups of children. One group had chosen to learn a musical instrument and the other one not. They were scanned at the beginning and then after 15 months of training. And what was found then was a time by group interaction, so that several of these anatomical phenomena developed in the musical group as compared to the non-musical group over time. And here Here's one example then where you have an increased volume of the precentral gyrus, and this anatomical effect was also correlated with performance on a bimanual motor task. Yes, and in general, the literature also supports that you have correlations between these anatomical phenomena and performance on tasks where you use the corresponding brain regions. Here's one example from the work of Peter Schneider, where they looked at the auditory cortex. What you have on this axis is the gray matter volume of the auditory cortex. They also then administered a fairly difficult test of musical ear, where you have to discriminate melodies and rhythms and pitches. It's Gordon's AMA test. Each symbol is a participant. You can see they were both musicians and non-musicians, and they found then a positive correlation between anatomy and performance. Well, quite a few years ago then, we were interested to see if you could see similar phenomena, similar anatomical effects in the connections of the white matter of musicians. So we compared in this study a small group of very concert-active Swedish pianists with a control group of non-musicians, scanned their brains with diffusion tensor imaging, and looked at the organization of white matter tracts. And I think what you see here is maybe the most important finding of that study, namely that in the pyramidal tracts, which of course are the main pathways, the main cortical pathways for control of fine finger movements descending down to the brain and spinal cord. In this region, we find a higher degree of organization, a higher fractional anisotropy in the pianists than in the non-musicians, and also relation between this measure and the amount of childhood practicing in this group. Here's another example. This is probably the most well-replicated finding, namely that the corpus callosum is larger in size, has a larger cross-sectional area in musicians. This has been shown in 4 or 5 studies, as I recall. This recent study is interesting since here they compared not just musicians and non-musicians, but 2 groups of players that had an equal amount of total practice, but one of the groups had started early in childhood, the other group later in adolescence. And still, when comparing these 2 groups, they found that the central part of the corpus callosum was more developed in the early trained group. And again, a correlation with age of onset of training. I already showed this study from Krista Hyde, but also here in this longitudinal study, it was found, if you recall, we had 2 groups of children. One learned to play an instrument and the other one not. In the playing children, as compared to the other group, there was an increase in callosal cross-sectional area here. So to summarize this little background, then I think it's clear it's clear that we have correlations between brain anatomy and musical training. We see this both in the gray matter and in the white matter. In part, these effects appear to be quite specific to what you actually do at your musical instrument, or what instrument you play, indicating that they are indeed expertise related. And there is also observational longitudinal data which indicates the kind of obvious thing that, in part at least, training must have a causal effect on the brain here. But most of the literature is cross-sectional. Of course, there is a very tricky issue about causality here. I think there has been a strong tendency in the literature that when we look at training and outcomes that are related to training, it's very easy to assume that we have a causal effect of training because it appears so obvious somehow. But of course, with the cross-sectional data, it's self-evident that several causal scenarios are possible. One would imagine that musical training influences the brain, but it's not impossible, of course, that if you have a brain where certain structures that are important for music are well developed, it's much more likely that you start playing an instrument, it's much more likely that you remain playing. So we can imagine the opposite causality. And of course, there's a third possibility, namely that some third unknown factor simultaneously influences both brain structure and the tendency to engage in long-term practice. And I just want to point out that, of course, this holds equally true for observational longitudinal studies, such as this very nice study by Krista Hyde. because these two groups of children had, so the musical group had chosen themselves to start to play an instrument, whereas the other group was then apparently not even interested to begin. So even though these effects develop over time, even though we see a difference between scan 2 and scan 1, it's of course quite possible that some other unknown factor is at play here, which has to do with the motivation and interest and abilities of these two groups. Genetic constitutions, for instance. All right, so you may ask, okay, so why not do a randomized longitudinal study, which is of course the golden standard to get evidence for a causal effect? Yes, it would be ideal in principle, but when we talk about expertise, we talk about very long periods of training, months of years, so it's often not realistic. Of course, we cannot randomize people into groups and then have them do motivated training on very complex tasks for such long times. So I would like to sort of illustrate that these are very general points and you will find them in any textbook, but it's a very real problem, and I would like to sort of give a case in point from the domain of music which illustrates that. So we decided to look closer then at one aspect of musical expertise, namely what you could call musical ear. So the ability to discriminate rhythms, discriminate melodies, discriminate pitches. And of course it's very important for a musician. It's well known that this is positively related to musical training. Musicians will outperform non-musicians on these kind of tasks, and it's also very common to assess these kind of musical ears when you apply to a music college. So we looked at this relation in a large cohort where we finished the data collection, well, it's 3.5 years ago now. So the data was collected from actually more than 11,000 twin individuals, and these were adults born between 59 and 85, so working adults. And this data collection was performed over the internet. So we collected a lot of data on their musical background, their musical training, their education, but also childhood variables such as parental support, peer interests, details about what education they had, and so on and so forth. We then measured using web applications, musical auditory discrimination, so how well they hear these musical sounds. General cognitive abilities, creative achievement, I will not have time to get into that, and also quite a bit of general psychology as well. And these participants are then part of the Swedish Twin Register, so we have also the possibility to look at a lot of other data which has already been collected in other waves of data collection from this group. So the simple question was then, what drives this association between training and musical ears? So the participants here we had more than 1,200 complete identical twin pairs, almost, you can see 1,350 dizygotic pairs, and then several thousand single twin individuals. And the variables we concentrated on here then were a measure of the total hours of musical practice, and this we calculated from self-report data then, so it's retrospective data. And then the results on a simple test of musical ears that included subscales measuring melodic discrimination, rhythmic discrimination, and pitch discrimination. And this was done by Miriam Mosing in our group. If we start then with the sort of phenotypic level, just ignoring completely that these participants are twins, just looking at behavioral data, we see then positive correlations between training, musical training, and performance on these tests. So these are our values of correlations. We have modest positive relations, as you would predict, and the tests also correlate with each other, suggesting that there might be some kind of general musical ear underlying this. But of course, the correlations are not huge. If you square these values, it's around 10% perhaps of the variance, which is explained by training. So again, a suggestion that if we talk about expertise in general, training is important, but other things probably matter as well. Okay, so we have this data then from twins, which means that we can use twin modeling to look closer at this relation. And just briefly then, for those of you who are not familiar with this, the basic idea of using twins here is, of course, that we have both monozygotic identical twins and dizygotic twins, and these have all grown up together in the same family environment in this case. So, in other words, the monozygotic twins will share all the genes and a common environment of upbringing, whereas the dizygotic twins are like ordinary siblings, so on the average they share 50% of the genes plus common environment. So the basic logic is just that if monozygotic twins are more similar in some respect than our dizygotic twins, this would indicate a genetic influence on that variable. And what you do today as a sort of standard method is to analyze this data using a structural equation modeling framework, which means that you can get estimates of genetic and non-genetic effects with confidence intervals, but even more importantly, you can also look at relations between variables and to what extent these relations are driven by common genetic and common environmental effects. So it's a very powerful framework. When Miriam then used twin modeling to look at these variables, she found first, if we just look at the univariate analysis, where you look at the variables as single variables, that there was a significant genetic influence on all three of these musical tests. So here you see the heritability, and that's simply the proportion of total phenotypic variance, which is explained statistically by genetic factors in total. So we have heritability is around 50% here. But interestingly, we also saw then that there was a substantial genetic influence on training. That is how much you train. So training is not, as it has been sort of perhaps discussed sometimes in the literature, some kind of entirely environmental variable that you can use to modify yourself. But how much we train in reality is influenced, of course, by our genetic constitution. And even more strikingly then, when Miriam made a bivariate analysis looking at the relation between training and musical ear, she found that this relation was essentially driven by genetic pleiotropy, so common genetic influences on these two variables. There was no significant improvement of fit when we added the environmental component. And if we look at the relation within the identical twin pairs, that's what you see here. So if you look within the monozygotic pairs at the relation between training and, this is showing Ruth as an example, but we show the same thing for all the subscales, the phenotypic relation essentially vanishes. So when you control for genetic and common environment, this relation no longer exists. So I think to the surprise of all of us, in this case, this kind of scenario seemed to be the main mechanism, that common genetic effects was driving this relation between one aspect of musical expertise and long-term training. So these are very real issues. That's the bottom line. Another interesting development in the literature in recent years is that now we have quite a lot of studies looking actually quantitatively at expert performance, some aspect of expert performance, and also including measures of how much the participants have practiced. So there's enough, there are enough papers out there for it to be meaningful to do meta-analysis, and the most comprehensive meta-analysis so far was made by Brooke McNamara and co-workers a couple of years ago. And what you see here is simply the meta-analytic estimate of how much of the variance in expert performance is actually explained by deliberate practice in total. And you can see that for music, it's a bit more than 20%, then leaving, of course, a lot of unexplained variance here. Now, of course, we will have measurement error and so on in this part, but it certainly leaves room for other variables than practice to play a role. And I think here we would need much more research. One study has found clear evidence for that in the case of music. One of these other variables is working memory, which predicts musical sight reading ability, even when you control statistical for long-term practice. But it would certainly be interesting to have more data on this. So we have recently tried to sort of synthesize this literature on music and also on other domains to propose a sort of alternative model to the deliberate practice framework. And we call this a multi-factorial gene-environment interaction model of expertise. So our thinking here was based a lot on music, but it's actually intended more as a kind of generic framework for that could be useful when you look at different types of expert performance. So it's schematically illustrated here, and we have the phenotypic level here in the upper part. So this model agrees then with deliberate practice theory that practice is a key variable in this context. Deliberate practice will modify neural mechanisms that are important for expert performance. This includes, for instance, sensory motor skills, and also, I'll come back to that a little bit, also these highly efficient interactions between long-term memory and working memory, which seem to be key to domain-specific working memory in experts. And of course, you may also modify certain physical body properties, muscle strength, and so on, which is important for expertise. But then, but then we also emphasize that traits, your personal traits, as well as environmental factors, of course, will influence your practice behavior. So, of course, interests and motivation will influence what you choose to practice and what you don't choose to practice. There's data suggesting that personality traits such as impulsivity influences practice habits. This has been shown for musicians. And abilities may well play a role too. Thirdly, then, we allow for practice-independent effects on expert performance of these various traits, in contrast to deliberate practice theory. And last but not least, I think it's very important to consider both genetic and non-genetic effects on essentially all these variables at the phenotypic level. And of course, this will probably involve a lot of gene-environment interactions as well as covariation between genes and environment, where if you have constitutionally an interest and an ability to perform, say, music, you will of course tend to search out and create environments that are conducive to your interests. So of course, we are interested then in testing predictions from this model further, and I think one key predictions where this kind of framework really gives rise to opposite predictions as compared to deliberate practice theory is, okay, so what happens with genetic influences as a function of long-term training? Because a key proposition of deliberate practice theory is that, yes, of course, various traits and genetic factors may be important for performance in novices and beginners, but as you train sufficiently, you will sort of circumvent this, you will wash away the effects of genetic constitution. So the prediction from the deliberate practice theory framework is that genetic influences on performance should diminish with training, whereas I think it's natural if you assume a framework such as the MGIM model I just showed you, that genetic influences would remain important even at high levels of expertise. So we recently tested this prediction in the same data set as I just showed you. So again, the outcome variably are this music perception or music discrimination tests. But what we look at here is then a moderator model. So what we test is how do the genetic and non-genetic influences on musical discrimination vary as a function of musical training? And you also take into account the correlation between training and performance. And as you can see here, the blue curve here represents the genetic part of the variance. Here you have music training. C is the common environment, the shared environment. E is unique environment, so this will sum up to 1 then. And as you can see, there was genetic influences remain even at high levels of training, and there's even a trend for them to increase in importance. So this analysis certainly supported our predictions and not predictions from deliberate practice theory. Okay, so it's very difficult then to actually sort of isolate causal effects of training when you are interested in expertise. But as I already indicated, I think twins can be a useful way to get at this problem. And basically then we can use the sort of discordant identical twin model. And the basic idea here is to, well, basically regard the twins as an experiment of nature. The point is that if there is a causal relation between training and some outcomes such as expert performance, we would predict that this relation remains also within the twin pairs. This is not real data, it's just to simulate the data to make the point. So in other words, if we plot the difference in training, the within-pair difference in training versus the within-pair difference in outcome, we would predict that this relation stays significant within the twin pairs if it's a true causal relation, as opposed to, for instance, a genetic pleiotropy. So, in other words, looking at discordant monozygotic twins is very interesting. And another strategy we have with this with this big data set is to find much smaller subsamples of twins that we think it would be interesting to look closer at and to scan also with neuroimaging and so on. So the first sample we have looked closer at is then a small sample of monozygotic identical twins that were highly discordant for piano practice in this case. So we located these people from this data set, and they lived at various places in Sweden, so we invited them to Karolinska Institute typically for a weekend of more intense testing. And in the end, we found only 10 pairs that were willing and could fulfill all inclusion criteria and so on, and were willing to come to Stockholm. And these pairs then differed more than 1,000 hours, and in reality more than 1,300 hours in total piano practice. The playing twin, so to speak, was still playing actively. The non-playing twin had played a bit in the childhood, but had not practiced in adulthood. So there was a long pause sort of in the practice here, and they were all right-handed, and they all fulfilled the sort of general inclusion criteria for MRI imaging and so on. And yeah, why didn't we look at completely discordant twins? Easy answer, they don't exist, not at least not in our data set. And of course, if you share both genetic makeup and the common environment, it's probably very unlikely that one of these siblings will not play at all, whereas the other one plays a lot. That's at least what we see in our data. So we were of course curious why they had become discordant, so we decided to look closer at that in a more exploratory way. I will show you a little bit what came out of that. So we performed longer semi-structured interviews with all these twins, trying to figure out why they became discordant. We made additional cognitive measures. I will show you a little bit from preliminary data from working memory tests. We looked at sensory motor abilities, and then we also performed various types of MR scanning, including both anatomy and some functional paradigms. So this is a bit preliminary data, but I thought it could be interesting to show. So yes, why did they become discordant? We have, of course, looked at predictors of musical training in the large cohort as well. And to make that story brief, it turns out that one quite strong predictor of musical training, now I'm talking about the whole twin cohort here, is the personality trait openness to experience. And as you know, that's one of the big 5 personality traits. It is actually strongly related to artistic interests, so that there are questions about that in one of the facets, and many other studies have also found that it predicts active engagement in the arts, so that we also see. Another trait, which I guess I won't have time to go so much into, but which we think is interesting in this context is, well, it probably relates strongly to intrinsic motivation to perform music. What we looked at here is how frequently these participants reported that they experienced psychological flow states while engaging in music. And as you may know, the term flow here was coined by Michał Csikszentmihalyi, the psychologist, and it refers to this state which we can experience when we engage in an active task that is challenging but not too challenging. I mean, what can happen then is that you become very focused, almost absorbed in the task, but it's a sort of subjectively effortless state of attention with very low self-awareness, and it's a very enjoyable and rewarding state. So when we asked these participants how frequently they experienced this specifically for music, this was actually of all the variables we have, by far the strongest predictor of musical practice. But of course, it's easy to miss a lot of things when you just run this kind of standard questionnaire. So we were really interested in also looking closer at these 10 twins that were highly discordant and performing interviews with them. So these interviews were organized around 5 main themes. Then first, we gave them opportunity to think freely about why they believe they became discordant. Then we asked more specific questions about differences in their sort of musical childhood environment, listening habits, teachers, interest of the peers, and so on and so forth. We asked about if there were any strong memories of music which they believe may have influenced their subsequent interests, what music means in your life, and we also asked a bit about linguistic interests. So it was clear then that, in general, the playing twins gave much more elaborate answers about the meaning of music in life, and only the playing twins gave answers which sort of emphasized that music is important for their personal identity, for who they are. This was not the case in any of the non-playing twins. But in general, otherwise, we found no systematic within-pair differences in any of these variables, in the interests of peers, parental support, music teachers, and so on and so forth. But rather what we found was that essentially each pair had a sort of unique explanation for why they became discordant. And these explanations could often be quite idiosyncratic, like, well, my sister had much more access to the piano, it was in her room. I liked the music played at home, but my sister didn't. We have different needs for creative hobbies. My brother liked the music teacher, but I didn't, and so on. So it seems then that perhaps it's a small data set, obviously, but when you control for both genes and shared common environment, you still have this sort of rather unsystematic, non-shared environmental influences, which are quite difficult to study in a systematic way. But in some cases, these are then sufficient to make one twin very engaged in music, so that music is an important part of life, whereas for the other twin is not the case. So it certainly supports this general idea in behavior genetics that non-shared environment, to a large extent, consists of these sort of unsystematic small microevents that also include perhaps stochastic biological events. So we looked at the short-term working memory capacity of these individuals, and the background here is really that it's well known from a large literature and expertise that experts show much higher working memory capacity, but specifically so for materials that belong to the particular domain of expertise. So this was first shown by Herbert Simon and his co-workers for chess, classical studies, and also earlier by Van Groot. So chess players have much better memory for chess positions, but this is quite specific for chess positions that can occur in games. So if you show random constellations of pieces, you will still see a slight advantage for the experts, but it's very, very small as compared to natural stimuli. And you can even show that if you compare people who have trained certain types of openings in chess as to those who are experts in others, you will see specific effects. And the similar phenomena has been shown for a number of groups. We see in musicians that musicians have much better short-term memory for musical notation, card players, taxi drivers, programmers, and throughout you see that this effect is very specific to if this information is organized in an ecological way. And of course, what must be going on here is very efficient, fast interactions between long-term memory stores and working memory. And we are very interested at the moment to look closer at how this works in neural terms. But what we did in our twins then was simply to compare their memory for musical stimuli and non-musical visual spatial stimuli. So the musical stimuli were simply melodic lines like this. And the task was just so we presented this for a couple of seconds, and then they had to reproduce it from short-term memory after a delay period. The control stimuli, here we used this kind of circular arrangement, so we had dots in different parts of this circular design, and the idea was that it would be difficult or impossible to somehow remap this into some kind of musical notation. And to show you then the preliminary data just from these 10 pairs, what you see, if we start with the right panel here, you see the performance of the non-playing twins, that's in blue, and the playing twin in red. This is number of correct responses, and here is the number of dots in the stimuli, 4, 5, 6, or 7. So these are the non-musical visual spatial stimuli where we found no significant difference between the twins. Whereas for the musical stimuli, in particular for the longer stimuli, which included in this case 8 or 10 notes, the musical twins significantly outperformed the non-musical twins. And this was significant even in this small sample. And here we are trying to replicate, we will replicate this in a larger group of twins. So it seems then that even though we control for genetic factors and common environment, you can still see these domain-specific effects on working memory. And we could also find some of the anatomical differences in the brain that have been found in earlier studies. This region here, the left temporoparietal junction area, had a larger volume in all the playing twins as compared to the co-twins. And recently we also finished a cortical thickness analysis confirming that this region has higher cortical thickness, and this we also see in the dorsal premotor areas. And for this region, there was also a relation between this anatomical effect and the within-pair difference in musical practice. We could also replicate the finding of a higher fractional anisotropy in the pyramidal tracts. This was significant on the left side in all the pairs. So these discordant monozygotic twins, I believe, provide unique possibilities to study pure training effects, if you like. So training effects that are independent of genetic factors as well as any common environmental factors that have influenced these twins. And what we have seen so far in this first analysis is that we have differences in brain anatomy in the temporoparietal junction and also then in the premotor area. We see it in the pyramidal tracts, and we also can see these domain-specific effects on working memory. Okay, so the final part of my talk then will be a brief example just illustrating how we can use music as a model also to look at creative cognition. And in this case, what we mean here is improvisation as a model behavior. And we think this is a nice model. It's sort of ecologically valid in that it's obviously a creative behavior by any definition. And it's possible to simplify and study in a brain imaging situation. Of course, we don't get the sort of real thing here, but something much more reduced. But we think it's still, enough valid to be musically interesting or relevant. And I just would like to focus on one question in relation to these studies, namely, what is the role of the dorsolateral prefrontal cortex for improvisation? And of course, this is a region which, as you know, is very important for cognitive control functions, attention, working memory, and so on. And what was puzzling for us here was that the literature was not consistent. So we have done several studies on classically trained pianists and where they improvise under different instructions. And what we see consistently is that the dorsolateral prefrontal cortex is more active during improvisation than during control tasks. In the first case, we used a control task where they played from memory. But you also see it when we use playing from a visual score as a control task, that dorsolateral prefrontal cortex is more active. But interestingly then, Charles Rimm and Brown looked at jazz improvisers, jazz pianists improvising, and reported very extensive deactivations of the prefrontal areas during improvisation. So of course we were very puzzled what's going on here. And of course one possibility could be that we are dealing with sort of specialization of the specialized here, that specific expertise, specific training in improvisation could be a key factor. So we tried to test this by looking at a sample of pianists that had varied background then. So some of them were pure classical players, some of them were pure jazz players, but we also had participants with mixed training in both improvisation and classical training. We looked at the brain activity during brief improvisations, 15 to 20 seconds, and the main question then was, of course, how does brain activity in this region vary as a function of improvisational training controlling for classical training? And indeed, what we found was that activity in the dorsolateral prefrontal cortex, as well as in the angular gyrus and inferior frontal cortex, was negatively correlated with improvisational training, to the extent that the most trained improvisers actually deactivate these regions as they improvise. So it seems then that training could be one explanation for this difference in the literature. What we also found in a follow-up study on the same data set was that characteristics of the instructions or of the tasks also matter. So what we did in this study was to have two different main conditions where they either were told to improvise in a particular mood, in a particular emotional mood, or to improvise using only a certain set of pitches. So they were only allowed to use a certain set of tones. And again, we see that when we constrain them to only use a certain set of pitches, it's quite difficult. They activate these regions much more than when they can do a more ecological improvisation in a given mood. So one speculation then could be that maybe we have sort of different neural strategies for creative thinking, in the sense that if you have a high level of task-specific expertise, if you are a trained improviser and if you are given a sort of ecological situation to improvise, you may need little top-down control, even in these creative tasks, which involves a lot of processing of new information and fast decision-making. Whereas if you're not a trained improviser, only a classical pianist, or if the constraints on your improvisation are novel to you, you will require top-down control. All right, so I will wrap up here. I think, the general point I wanted to illustrate is that artistic behaviors and artists as models are interesting when we are interested in higher human cognition in general. When it comes to expertise, I think there has accumulated strong evidence in the last 5 years, say that we have to think about expertise as a multi-factorial phenomenon where practice is important, but also other variables at the phenotypic level, and where gene-environment interactions play a key role. So more data from genetically informative samples would be very important, of course. We also use music to try to get at neural mechanisms of creativity, and here it seems that prefrontal involvement in creative thinking is dependent on your specific training and on the task characteristics. So just to highlight some of the people who did the work, Miriam Mosing and Karin Wei do the twin modeling in our team, Örjan de Menzano and Anna-Luisa Pin, who were main people behind the imaging data. And we collaborate then with Nancy Pedersen at the Swedish Chain Registry and Therese Turell and Guy Madison at KI and Umeå, respectively. All right, thank you very much.
Much, Fredrik. Questions? Yes, George first. Microphone comes from the left side.
Well, that was quite a trip, an exploration. I have a question. Have you compared, in essentially the same area, what happens with painters, for instance, with artists of other disciplines besides music, like painting, or I was thinking about cooking because it's an art. But well, do you know any study, and if there are any differences?
Right. So no, we have not done any imaging on painters. I don't know, it's probably quite difficult technically. What we have looked a bit at in the twin data is creative achievement in other domains as well. So we have data there not just from music, but also from painting and theater and dance and literature, as well as from science and innovation. And what's clear, if you look at individual differences there, is that the sort of artistic and scientific forms of expertise are very different, both in terms of phenotypic correlations and in terms of genetic underpinnings. So it seems that the artistic domains form one cluster, and science and innovation, another cluster. But then you have also domain-specific differences, which are interesting. For instance, visual creativity is more strongly related to schizotypic personality than some other forms. So yeah. But as for imaging, I don't know. And I'm not aware of any study looking at painting in the scanner, no.
So, Wolf?
In the twin studies, did you find more discordant twins among the male twins as the female twins, or the other way around? Was there a difference? Because of this chaperone thing in the X chromosome inactivation in girls?
No striking difference. That I recall in the 10 pairs we had roughly equal numbers of males and females, these extremely discordant pairs. We have sometimes found sex differences for pitch processing. So there we have some indication that the genetic influences may differ between the sexes, but you need a lot of power to look closely at that. So, I don't know.
There was first a question over there, and then the microphone comes to me.
Okay. So my question is that we talk about creative thinking, and yesterday also talk about input-independent, self-organized brain. So I do not know whether this creative thinking is some output of this self-organized brain. Is it something related to the feeling of self? I mean, many animals may not have a feeling of self, but for human, we do have a feeling of ourselves. So I don't know whether the creative thinking has something related to this self-organized brain or the self-feeling, something like that.
If creative thinking is related to thinking about yourself, it's a difficult question. I don't know really. I mean, it's also, of course, obviously creativity is a rather dangerous concept, and the sort of very general definition would be that you come up with novel things that are still functional or useful, which could involve a lot of things. So I prefer to sort of just use operational definitions like improvisation, which is quite clear what you're looking at anyway. I'm not aware of any evidence for this. Maybe I didn't understand the question quite, but we can discuss later, perhaps. Yes.
Very, very nice talk. At one point, you showed this area, parietal temporal area, that was affected.
Yeah, this SPT thing. Yeah.
It's SPD, or
it
would be interesting to give you our other area to see. What happens there.
And we should also look closer at the functional data, but of course, I'm afraid we may not have sufficient power to.
No, but we could give you the coordinate. You could.
No. Would be happy, of course. Yes.
So Zoe.
Yes, I was wondering whether you had. I'm here.
Hi.
You had looked into features and how they may react to music, because if there is a genetic.
Unborn.
Unborn. I mean, they react for sure, but maybe there is a genetic determination that...
we have not looked at that, so we are only looking at adult participants actually so far, so I can't say. Yeah, but there's some data suggesting this, but I'm not sure how well corroborated it is actually, but yeah.
Wolf?
I have always been struck how difficult it seems to be for classically trained musicians. If you take away the paper and ask them to simply harmonize blues or something to accompany other people or to improvise, is it only dorsolateral prefrontal cortex, or is there some other basic difference in what they organize and what they learn? Because technically they should be able to perform virtually everything. Don't they hear it? Don't they continue to hear things when they have no written notation in front of them, or what is the problem here?
I would, to me, it just illustrates that expertise is really an extreme process of specialization. I mean, you adapt everything to the particular tasks that you train. So I would guess you see differences at many levels. I mean, we haven't looked closer at that, but one idea we have is also to compare musicians from not oral but sort of non-written traditions, like folk musicians, to people who sort of grew up with a score like me, and to look closer at these things. So I think, expertise is a specialization process really. So I would expect adaptations at every level. Yeah.
So there was a question there, and then
I wanted to go back to your sample of your monozygotic twins.
Yeah,
Was there any cultural variation? The cultural variation of your population? Were there mostly Western European twins, or were there?
Yeah, so they are all ethnically, they are all sort of Westerners, yes, and this and they have grown up in Sweden, so it's culturally quite homogeneous, yes.
So I'm going to ask you to speculate. If you take, say, the MZ twins that are raised in the People's Republic in China,
yes,
and trained in the musical tradition of PRC, which is quite different from
in the Western tradition. Or
that's right. No, they're trained in their, they're raised and grown in their tradition. Would you see the similar training effects if they cross over, or would I mean, just speculating? I understand.
Yeah, my speculation is that you would see similar phenomena, but of course, okay, when we look at musical scores, we use Western scores that they have trained. So if we look, I mean, the key when you study expertise is really to tap into tasks that are as ecological as possible for that domain of expertise. So I would probably in that case use, well, of course one should use tasks that are sort of ecological for a person trained in traditional Chinese music, but if you look at some of these brain findings that involve the pyramidal tracts and auditory motor regions, yeah, of course, the natural guess is that you would have them there as well. So some differences and some overlap, I guess, yes.
So many questions. Next one, you.
Thank you very much for the talk. Going back to the results on the dorsolateral prefrontal cortex, it's very interesting because it mirrors other results from study of general creative cognition, where in studies of ERP or even just psychometric studies, they show that when you measure expert creativity, you get different characteristics compared to if you measure it in terms of task creativity, like divergent thinking tasks and the like.
Yes. Yes.
And it's very interesting that you speculate that maybe this has something to do with the fact that ecologically valid expert creativity requires less top-down control compared
to me, this is a rather non-trivial finding, because we tend, I mean, it's not obvious that you could automate this kind of task, right, which involves sort of de novo production of musical materials online and a lot of decision making and so on, but still we see this rather dramatic relation. So yeah, no, I agree, yes.
But would that mean that, would you think that those kinds of more puzzle type of measurement of creativity might be less useful than we thought? Given
you mean
this?
Like creativity tests and stuff?
Yeah, those kinds of things, because they are not always.
No, and I think that the sort of predictive validity has never been that impressive, has it? I think there's something there, but I mean, in terms of actual R values, it has always been quite meager, I would say. So yeah. I agree. I'm more interested in ecologically valid forms. Yeah.
Just one last thing, is the 10,000 sample study, will you make that available for other researchers, maybe?
You mean the data?
Yeah, the one, the big one.
Yeah, no, we are always very open for any kind of collaborations if you have a question, of course.
Yes.
Yeah, no, absolutely. I mean, we haven't sort of made the data public, but that might well happen later on.
So, Stanislas?
Yes, I wanted to ask you about the role of Broca's area in music, and especially perhaps in this improvisation task. It didn't seem that Broca's area was being activated. I would have expected perhaps it would show up when there is a phrase structure in the music.
Yeah. No, we see inferior frontal cortex regularly. What was shown there was just the regions that decreased in activity with training. No, we see both Broca and pre-SMA regularly when we contrast improvisation with more predictable tasks. And what can I say? I guess it has to do with sequential organization of behavior in general. I mean, I think there are several studies showing that it's involved in music and also plasticity in Broca in musicians as compared to non-musicians.
No, so that could be very interesting then with respect to the previous discussion.
Yes.
Maybe you see a decrease in conscious control with a decrease in dorsolateral prefrontal cortex, maybe replaced by a more automatic unconscious syntax in Broca's area.
Mm. Yeah, no, it's very interesting how yes, how it is organized without with so little contribution from prefrontal cortex. Yes.
So, Jacob.
I was trying to put myself in the shoe of this guy lying in the scanner.
Yeah.
So if I have to do en promptu, so at the beginning I will do some chords which are already in my working memory, because I cannot start from nothing. So the beginning will be obviously something related to my past experience. My creativity will start later. So maybe you can either eliminate the first part of improvisation, or to have another technique in which you have time. Because time could be very critical. At the beginning, of course, you have to start with something that you already know. Then you modify. Maybe jazz players are different, but for a classical music, I think that should be the strategy.
Yeah, it didn't. I don't think it was not striking anyway when we looked at what they actually. I mean, these are professional musicians. I didn't feel that they were very inhibited in the first trials, but I guess we could look at it. Yeah.
But you tried to go inside.
Me, yes, yes, of course.
So what you do when you start to create this?
You mean in the very first trial? Well, it will depend. But I'm so primed. I developed these paradigms and all. I don't feel this problem that it would be difficult to begin with. But certainly one could look at that. Yeah, eliminate the first trials. But.
Yes. Now the musicians, please. Finally, Bernard.
Thanks. I'm curious if you've done a study where someone was reimagining the same phrase, deliberately conceiving it differently. So in other words, trying to be creative within the same material. Because I find, from a performance perspective, that's an interesting psychological game, if you like.
You mean you take a single phrase and then you play it in different expressive modes?
So for example, deliberately, not prejudging that. So in other words, just asking someone to imagine a phrase and now imagine it differently. So that the creative energy was not in creating material so much as thought process linked to the same material.
More on the perceiving side, you mean? Or?
Exactly. So therefore, more.
Yeah, no, we haven't done that.
Okay.
It's an interesting idea.
Yeah. Thank you.
Hi, Professor.
Hello.
I was wondering, across your research, did you find you did many findings in different ways that musicians train? Like improvisation, score memorization, and things like that. So do you propose any model for young musicians to uptake when at the start of their musical training? Because many times, like when I was younger, I don't really remember how I trained, but it was many hours just sitting in front of piano with one piece and just repeating it over again. And I'm not very sure if that's very efficient. So do you propose any more efficient models?
When it comes to how you practice and this kind of stuff. It's not something we have looked at, but I think there is relevant data out there. For instance, Anders Eriksson has looked a bit on that, and one thing he has found was that that this was when comparing German music students, that the sort of students which were rated as best then tended to organize their practicing differently. It's not just about the amount of practice. So they had, if I remember correctly, they had shorter practicing sessions and then pauses in between. They more often actually took a nap in the middle of the day. They slept a bit more than the less good ones. So it seemed, so the interpretation here was that what's really important is that you practice in a highly effective way, that you are really focusing a lot, that you know what you want to do, that you are very goal-directed, and that you avoid simple repetition behaviors and so on. And this I completely subscribe to. I mean, I think it's extremely important that you, and also more fun actually, that you know what you want when you practice. So, but there's more to say there. I mean, variation is probably good.
Thank you.
Further questions? Oh, Paul.
I just want to go a little bit laterally here. So, you've done this with musicians, and you have this data now. What about comparing hockey players? Take the Swedish hockey players who are very expert, and put them into. I mean, if we want to extrapolate about what is going forward here in terms of musicians.
Yeah.
You hear what I'm saying?
Yeah, I hear what you're saying. So Yes, I mean there are a lot of anatomical studies on different experts groups, and you will typically see effects that are somehow in regions that are useful for that form of expertise, and I'm sure you could see that in hockey players as well. If you ask me what I think is the most interesting next step, I think we need more functional data, and one thing we want to focus on is this interaction between long-term memory and working memory in experts. And what in one study that we are starting up now, we will compare musicians with chemists, actually, and with chemists. And the idea is to look at encoding and working memory for chemical notation and musical notation to see how this is represented. And we predict, of course, a more multimodal, redundant representation in musicians than in the chemists. But yeah.
More questions? So, Fredrik, I was really impressed, not surprised, but impressed by the fact that the age versus practice time curve is extremely similar to the maturation of the pyramidal tract, the myelinization pattern, which reaches its maximum at age 25. So our pyramidal tract is not fully myelinated until age 25. Shows an extremely similar curve. So it somehow shows that some other neurophysiological or neuroanatomical underpinnings.
Although I think that might be epiphenomenal in the sense that it's very typical that that training decreases when you reach sort of older adulthood, but I think it has to do with a lot of other things happening in life, and you have less time and so on and so forth. So.
Sure. Further questions? Oh, Ernst.
The Mozart effect, I think it died, sadly, yes. No, I'm joking, but I don't think, I mean, it was a while ago that I looked at that literature, but my memory of it is that there is no evidence for a specific effect of listening to Mozart. There is some evidence just for a general arousal effect that you can evoke with other stimuli as well, and a lot depends on which baseline task you use and so on and so forth. So, no, I'm not a believer. No.
So, any further questions? So I should make a comment that Fredrik and I have now a joint PhD student between NTU and Karolinska, who is also a musician, Kasia Lumanting, and she will study under Fredrik some of these things, and we will apply her knowledge here in Singapore in the imaging center. It will be absolutely fantastic, Bernard, that your people would join us, because we will have this imaging, or we have already this imaging center, cognitive neuroimaging, and put your musicians and see how.
Maybe we could mention what it's about. I mean, this project will focus on selective attention in a polyphonic musical context, because of course it's a very interesting phenomenon that you are able, as a musician or as a listener, to focus on one part in a polyphonic structure, even if it's not spatially segregated. So you can sort of pay attention to the top line or the bottom line or the middle line. And we would like to study the mechanisms of this using MGIM and frequency-tagged auditory stimuli.
And I'm sure that the cocktail party effect, which Fredrik talks about,
it's a bit different.
Different, because we know from other studies done at NTU that, for instance, Chinese children or those people who were grown up in a Chinese culture have a very different figure ground segregation mechanism, fundamentally different than what we have in the West, where we always focus on something which is in the focus of our attention, whereas the Chinese, the native Chinese listener or perceiver is seeing everything with equal weight in the picture. So I can imagine that in the cocktail party effect, those who are brought up in another tradition have a very different mechanism than those who were brought up in, say, in our traditions or anyway. Oh, Carlos.
Yeah, I don't know why I got to think about this, but have you thought about testing conductors, not practicing instrument, people practicing an instrument, but a conductor, and would that, I was thinking about this, of this polyphonic, because that would be the opposite, that a conductor is thinking about all the voices at the same time, and would there be any value in looking at that?
Yeah, no, I think it's an interesting group, and I believe I've seen at least one study on this and on sort of auditory ability to spatially segregate sounds in conductors, but I'm not quite sure that. No, I think I would have to develop some more specific question then, but it's certainly an interesting group. Many conductors, of course, have a strong background as instrumentalists, so that's a confirm.
Oh, Henrik.
Yeah, we've discussed this, of course, but we don't have any specific ideas for a paradigm right now, but it would be interesting. This, again, I'm not aware of any studies on this group, which of course is, it would be interesting, yes.
So, if there are no further questions, Fredrik, this was really absolutely great, and thank you. Thanks again for the talk and the concert, Thank you. We convene again at 10:45.